The objective of this video is to work through a couple brief examples of inverter analysis. In our first example, suppose we want 120 volt AC RMS with a modulation index of 0.45. What is VDC for a half bridge? That is, what is our required throw voltage for a half bridge converter in order for us to get 120 volt AC RMS out with a modulation index of 0.45. Press pause and press play when you are ready to resume. So we've previously talked about, for a half bridge inverter, our output voltage is equal to M times our DC bus value times the cosine of the quantity, times the cosine at the frequency that we're trying to output. And so we can solve this expression for MVDC equals square root of 2 times 120 volts. And the square root of 2 is something you have to be careful about in this class, because remember that that only comes into play when you're dealing with pure sinusoids. But in this case, we're assuming that we've got a pure sinusoid that we're trying to create with a modulation index of 0.45. And so if we solve this equation, we end up getting a DC bus value. That's about 380 volts. In our second example, we have a three-phase inverter with 120 volt RMS line to neutral output voltage that is feeding a motor which has a 1 horsepower load. So we've got our inverter attached to a motor which is attached to 1 horsepower load. And we're told that our motor has energy conversion efficiency of 90% and that it's operating with a power factor of 80%. What is the phase current of the connection from the inverter to the motor? How much current is flowing in one of these phases? So press pause now and press play when you're ready to resume. So first we can convert 1 horsepower into watts. So in electric motors, we oftentimes work in both horsepower and watts. You have to be familiar with how to convert back and forth. And 1 horsepower is approximately equal to 750 watts. And that is our mechanical output power. Our electric input power is going to be the mechanical output power divided by efficiency, which is approximately 830 watts. And we've got 3 phases, which means that the power in each phase is about 275 watts. And from here on out, we can use the expressions that we talked about in the beginning of this class about relating real power to apparent power and power factor. So if you recall, apparent power is simply equal to our RMS voltage times RMS current. And we're talking about a single phase system here. So if we have one of these lines, we can talk about the line to neutral voltage times the line current is going to give us our apparent power. And our real power is going to be our apparent power times the power factor. So in this system, we can determine our volt ampere input, which is our apparent power, as being our power per phase divided by the power factor, which is 80%. And that gives us an apparent power of about 345 volt amperes per phase. And then we can relate this back to current input by this expression right here. Next, consider that a 3-phase inverter is generating the following line to neutral voltages. So we've sketched our inverter over here, and V1, the line to neutral value of V1, is 100 times the cosine of 2 pi ft. And V2 and V3 have the same magnitude but are phase shifted by 120 degrees. At time 2 pi ft equals 60 degrees, so at a value of t so that this expression evaluates to 60 degrees, what are VP1, VP2, VP3, and our 3 duty ratios if we have a DC bus of 300 volts? So press pause and press play when you're ready to resume. We've been talking about how the pole voltage in these converters has a bias value of 1/2 of our DC link. So if this is our DC link, our throw voltage, the pole voltage is going to have a bias or a common mode component of 1/2 of that. So that means that this is going to, VP1 is going to be equal to VDC by 2 plus the desired output voltage that we want at this instant of time, so plus V1. And we can evaluate these expressions up here at the value. So in this case, this is evaluated at 60 degrees. This one's evaluated at 60 degrees minus 120, so it's going to be negative 60. This is going to be 60 degrees minus 240. And if we do that, we get the following values. We have 50 volts, and negative 100 volts. And so now we're ready to populate this expression down here, and we end up with VDC by 2 is 150 volts, and V1 at this instant of time is 50 volts. So we end up with an output pole voltage of 200 volts, which we can convert to a duty ratio of 2/3. We can repeat the same exercise for pole 2 and pole 3. So clearly pole 2 is going to be the same as pole 1, so you're going to have 200 volts and a duty ratio equal to 2/3. And then pole 3 is going to be 150 volts, now minus 100 volts, so you'll have a pole voltage of 50 volts, even though your line to neutral voltage is negative, which gives you a duty ratio for this pole of 50 over 300, which is equal to 1/6. So in summary, we've gone through a few examples, simple examples, applying the analysis and topologies of inverters